Here's a first example of a continuous distribution. We have a spinner. You can see an arrow which, when spun in a frictionless zero-gravity environment, and if we measure where it lands with infinite precision, this being a very difficult physical experiment to execute, it determines a random variable capital X, which will be a random number somewhere in the interval between 0 and 1. We chose a zero-gravity environment so that any interval between a and a plus h of length h would have the same probability regardless of where it's located, regardless of the value of a. In other words, the probability of an interval depends only on the width of the interval, not on its location. And it's easy to see that the cumulative distribution function is given by f of x equals, well, let's begin with a value of x between 0 and 1. Such a value is labeled on the graph. It looks like it's somewhere around x equals 0.4. Then the probability that the spinner lands in this region, shaded yellow, is given by the fraction of the total circumference that represents, which in this case is the ratio of x to the total circumference, 1. So the probability that the spinner lands in that region, the probability capital X is less than or equal to little x, is given by little x itself. That's the middle value in this table of possible values for f of x. What if x is minus 1? What's the probability capital X is less than that? Clearly it's 0. In fact, it's 0 whenever little x is negative. What if x is 3? What's the probability capital X is less than or equal to 3? Well, it's obviously 1, since that includes all the value that capital X can take. Indeed, for any little x bigger than 1, f of x equals 1. The cumulative distribution function lists the possible values of the probability x is less than or equal to little x for all values of x, all real numbers x, including, in this case, negative values and values bigger than 1. The corresponding probability density function. What if I were to take the derivative of capital F of x on the previous slide? Well, for values of x that are strictly less than 0, the derivative is 0, because the CDF is flat there. For values of x bigger than 1, again, the derivative is 0, because the CDF is again flat. For x between 0 and 1, strictly between 0 and 1, the value of f of x is x, and the derivative of that is 1. So we've identified the probability density function from the derivative of capital F of x, except for a possible complication at the points x equals 0 and x equals 1. At these 2 points, capital F of x is not differentiable at all. We don't know what value to assign to little f of x. Indeed, in this graph of the probability density function, it's not clear what value little f of x is to take at the points 0 or 1. It's not labeled. And the reason is that it doesn't matter. You could let f of 0 be 1 and f of 1 be 1. Or you could assign both little f of 0 and f of 1 the value 0. You've changed, in any case, a function little f of x at 2 points, x equals 0 and x equals 1. Can that make a difference to any integral over an interval involving the function f of x? A change at 1 or 2 or any finite number of points will not alter any integral. It doesn't alter the probabilities, therefore. So either of those 2 definitions of the density are adequate to specify correctly this distribution. You may start with the cumulative distribution function, or you could start with this probability density function described here and use that to determine probabilities. For example, the probability that x is between a and b is the integral from a up to b of f of x dx. Or if we wanted to obtain the cumulative distribution function from this density, we would integrate from minus infinity up to b f of x dx. Remembering, of course, in this case at least, that the integral from minus infinity to 0 contributes nothing, since the density function is 0 over that region. General properties of a probability density function. The first we've already seen. The probability that x falls in an interval between a and b is f of b minus f of a in general, capital F of b minus capital F of a. And that can be written as the integral from a to b of the probability density function little f of x. This, in fact, is the definition of the PDF little f. Probabilities are non-negative. And so when I integrate over any interval, f of x should also be non-negative. Little f of x is greater than or equal to 0. Little f of x could be equal to 0, as we've seen in the previous example, in a region where values of x do not occur. The sum over all probabilities is 1. And similarly, in this case, when I integrate the probability density function over the whole real line from minus infinity up to plus infinity, I must obtain an integral of 1. The area under the PDF, the graph of the PDF, is 1, because the probability x falls somewhere between minus infinity and plus infinity is 1. And the fourth property on this slide is just a reminder of how to get the CDF, capital F, from the PDF, little f, by integrating from minus infinity up to y of the PDF. And in reverse, if you're given the CDF, you can differentiate it to get the probability density function, uniquely defined except possibly at a finite number of points, as in the previous example. There were points at x equals 0 and x equals 1 where the derivative did not exist. Here's a review question. If x is a continuous random variable with probability density function little f of x and the cumulative distribution function capital F of x, which of the following statements is false? Little f of x equals capital F primed of x for all values of x. B. F of x is greater than or equal to 0 for all x. C. Capital F of x is a continuous function. D. As I let x go to infinity, capital F of x approaches the value 1. And E. Little f of x is equal to the probability capital X equals little x for all values of x. You should pause for a few minutes and determine which of these statements you believe are true and which are false. Let's examine them one at a time. First, A. F of x equals f primed of x. We've seen that may be false for a finite number of values of x. In general, it's a true statement. But for example, in the case of the spinor PDF, there were 2 points x equals 0 and x equals 1, where the f primed of x did not exist. B, the probability density function is always greater than or equal to 0, so that's always true. C, f of x is a continuous function, and that's simply because f of x is the integral of the probability density function little f of x. D, the limit as x goes to infinity of f of x equals 1, that's just a statement that as you integrate the density function up to the value x, and then let x go to infinity, you end up with the total area under the density, which is always 1. And finally, E, f of x is the probability of that value x. For a continuous random variable, we've seen that the probability of any one value is 0. That can't be true, therefore. That's false because f of x is typically not 0. It's certainly not 0 at all values of x. f of x does not describe the probability of a given value. What it does do is give you the relative probability of values near that in different regions of the sample space. Review question 2. Consider a random variable x having a probability density function f of x equals k e to the minus 2x for positive values of x, but f of x is equal to 0 otherwise. And k is some constant that has not been given to you. The first part of the question is to find what an appropriate value of k is. You should pause for a moment while you answer this. Well, what do we know about probability density functions? This is certainly a non-negative function, and the total integral of f of x over the interval from minus infinity to infinity should be equal to 1. Well, we can discard the portion up to 0, since it's 0 there. The integral from 0 to infinity, k e to the minus 2x, is k over 2. And so, in order that that be 1, k must be 2. The second question is, find the cumulative distribution function for this distribution. Again, pause while you solve this. Let's start by getting the cumulative distribution function for a value of x which is positive, in which case f of x is the integral from minus infinity to x of little f of x, or the integral from 0 up to x, 2 e to the minus 2z dz, which turns out to be 1 minus e to the minus 2x. So the cumulative distribution function, when x is positive, is 1 minus e to the minus 2x, and when x is negative, of course, those values of x are impossible for this distribution. F of x is equal to 0. The third part of the question is to find the probability that x falls in the interval between 1 and 3. Again, pause while you work out the solution. This probability can be most easily written as f of 3 minus f of 1, where f is the CDF we calculated in part 2 of the question. 1 minus e to the minus 2 times 3 minus the quantity 1 minus e to the minus 2 times 1. And that works out to minus e to the minus 6 plus e to the minus 2, or numerically a value of around 0.133.